Okay, there's nobody here yet, but I am still going to continue with this class. You can catch a playback on YouTube to see what you may have missed. So the last time we were here, we were talking about Lewis structures, and we talked about the steps that you'd have to go through in order to get the Lewis structure for a molecule. So the steps are listed here. Whoops, sorry. But of course, just reading this will not help. You have to actually do some examples to understand the steps involved. So we did a couple of examples, which I can't remember right now, but I remember they were relatively simple examples. So now we're going to do some more examples, and you're going to see that the examples will become more complex as we go along. So what I'm going to do is get out of here. And what shall I do? What shall I do? What shall I do? Let me go to my writing pad here. And let me scroll down a bit. Okay, so the next example, let me choose my pencil here. Also what I should do is share my screen. How could I forget? Okay, so I'm hoping that the screen will be visible to all. So the first example we're going to look at for today is that of phosphorus. Oh, shucks, what's going on here? Phosphorus trichloride. And if you remember, the first step is to count up the total number of valence electrons. So if you go to the periodic table, you see that phosphorus will contribute 5 electrons, and the chlorine will contribute each 7 electrons, but there are 3 of them. So that would be 21 electrons. So therefore, the total number of valence electrons would be 26, which is the same thing as 13 pairs of electrons. Then we put the phosphorus in the middle, which is the least electronegative element, and we surround it with the chlorine. And then now remember, we have 13 pairs to assign. The first 3 would be the 3 bonding pairs here, here, and here. And then the next pair of electrons would go on one of these chlorines, then 4, actually that's 5, 6, 7, 8, 9, 10, 11, 12. So we have one more pair, because remember we have a total of 13 pairs, and that pair would go on the phosphorus atom. So this would be the Lewis structure of the compound phosphorus trichloride. All right, so that's another relatively simple example. Okay, let me move on to something a bit more complex. Now, let me remind you of something I said the last time, and that is the formal charge, right? The formula I gave you, if you look in different textbooks, you'll see different formulas, but the one that I gave you, which is the one that I prefer, is that the formal charge is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons. This is the formula I gave you guys for calculating the formal charge. And this calculation should be done for every Lewis structure, for every atom in every Lewis structure that you're trying to determine. And you're going to see in the examples that I'm going to look at right now where it is important. Let's deal with carbon dioxide. So again, we do like we did before. We count up the valence electrons. So carbon will contribute 4, oxygen will contribute 6, and there are 2 of them, so that would be a total of 12 contributed by the oxygen. So therefore, the total overall will be 16 electrons, which will be equal to 8 pairs. So we have 8 pairs to assign. We put the carbon in the middle, surrounded with the oxygens, and then we put the bonding pairs, 1, 2, then the non-bonding pairs, 3, 4, 5, 6, 7, 8. So we have used up all the pairs of electrons that we have at hand. The next step is to calculate the formal charges. So using this formula up here, we're going to calculate the formal charge first for the carbon. And that will be equal to the group number of carbon, which is 4, minus half the number of bonding electrons, which is half of 4 minus a number of non-bonding electrons, and carbon has no non-bonding electrons. So therefore, this gives you a total of +2. So the formal charge on the carbon here is +2. We're going to do a similar calculation for each oxygen. And if you look at each oxygen atom, they have the same electronic arrangement as far as their valence electrons are concerned. So we can do one calculation for both oxygens. And that would be group number, which is 6, minus half of 2 electrons, minus a number of non-bonding electrons, which is 6. So this works out to be equal to -1. So each oxygen has a -1 charge. So here we have a situation where we have a carbon, which has a +2 charge, directly bonded to, on either side to one oxygen on either side, each having a negative charge. So what's going to happen in this case is that this pair of electrons here from this oxygen will come down here to form another bond. The result of that is that this negative charge will cancel out one of these 2 plus charges. And then this pair of electrons will come down here. And the result will be that that negative charge will cancel out the remaining plus charge. So therefore, the final answer for this would be so this here would be the Lewis structure of the carbon dioxide molecule. All right. So that's basically how that is done. Let me see something here. Okay, what's going on here with this? Okay, so move this aside. Okay, so that's basically this example actually shows the reason why we need to calculate the formal charges, because as you can see in the case of carbon dioxide, and you'll see in case of other molecules, there may be the need for the formation of multiple bonding. In this case, a double bond right here and here, right? And the only way we were able to determine that is by determining the formal charges in the first place of all the atoms in the structure. Okay, let me move on to, well, before we move on to that, there are a couple of things I want to cover in the PowerPoint before we move on to some other examples. I'm going to talk about here about certain molecules that do not obey the octet rule, all right? So if you look at this molecule here, this molecule is, this is the Lewis structure of nitrogen dioxide. So if you go through all the steps that we did, then you'll end up with either this or this structure. They're both equivalent, basically. Now, what you'll notice is that there is an unpaired electron here on the nitrogen atom, which means that the nitrogen here will not have 8 electrons on its outer shell. It will have 2, 4, 6, and then this one here makes it 7 on the outer shell, right? And that's basically as a result of the actual number of electrons that we can assign. There's no more than, there's no more electrons we can assign to the structure, so therefore we end up with a structure where we have an unpaired electron on the nitrogen, and therefore nitrogen does not have 8 electrons. We call this type of structure, we call it a free radical, right? Any structure, any molecular structure that has an unpaired electron on any atom, pretty much, we call it a free radical. Let me write that term down here. Free radical, all right? And free radicals are very important, especially for those of you who plan to do organic chemistry. You'll be meeting these structures a lot. They're very reactive, and they can influence certain reaction pathways for certain compounds. That's all I can say about that. I won't go into details concerning that. So this is one example of a molecule that does not follow the octet rule. Another example would be a molecule like this, boron trifluoride. And if you look at the boron right here, you'll notice that the boron atom has 246 electrons on its outer shell. So therefore, it does not have an octet. And again, that's a consequence of the sheer number of electrons that we have to assign. Now, what can happen, as you can see here, is that a pair of electrons from the fluorine here, let me put this here, can be donated here to form a double bond. And therefore, the boron can end up with 8 electrons on its outer shell. But it's not always possible. So for example, if you look at this molecule here, if you replace the boron with hydrogens, you'll notice that, well, there's no pair of electrons on the hydrogens lone pair that can be donated to form a double bond anywhere. So therefore, this is basically the structure of the boron trihydride molecule. That's another example of a molecule that does not obey the octet rule. Now, one remarkable thing about this molecule and this molecule is that because it is short 2 electrons to get a complete octet, it is very active, and in its reactions, it will try to react with species so as to get those 2 electrons. So for example, and I'm just using the chloride ion as an example. The chloride ion has 8 electrons on its outer shell, 4 lone pairs, and therefore you can have a pair of electrons donated to the boron here, and you end up with this molecule. Well, actually, it's going to be an ion. Where there's going to be a negative charge here, all right? So that's the behavior of structures such as these, which are deficient in an electron pair, where in one of the atoms of the molecule, it will seek out basically any species that has electron pair so that it can have its octet satisfied. Okay, so that's another example of a molecule that does not follow the octet rule. And here is yet a couple of examples of other molecules that don't follow the octet rule. Now, in these cases, the central atom will have actually more than 8 electrons, right? 2, 4, 6, 8, 10 in the case of phosphorus pentachloride, and 2, 4, 6, 8, 10, 12 in the case of sulfur hexachloride, all right? So this is possible for certain central atoms, and the type of central atoms that will display this sort of arrangement are, let me write this up here, atoms from period 3 and higher periods. So in other words, period 3, 4, 5, etc. All right. This will not occur if the atom is from periods 1 and 2. Okay. So in these cases, as I said before, the number of electrons on the outer shell for the central atom is actually more than 8. All right. And the terminology that is used in some textbooks is that these atoms can expand beyond the octet. And there's a reason for this, which we won't get into until next chapter, actually. Okay, let me see here. Oh, Dalton, you're here. Can you hear me?
Yes, sir.
Okay, good, just checking. All right, I started without you because I know it's being recorded, so if you guys missed it, you can catch the recording on the playback. I'm sorry?
It said I didn't have, the Zooms weren't uploaded to the schedule, so I was looking for how to get back onto it, and I see you just uploaded.
Yeah, yes, yeah, that's my, yeah, thank you. Yeah, I didn't realize that I didn't create a Zoom link until this morning. Okay, sorry about that. So that's basically what we're talking about. Here we're talking about molecules that don't follow the octet rule, all right? Let me backtrack a bit since you just came on. So there are certain molecules, as I said before, that don't follow the octet rule. This is one example. If you look at this nitrogen here, it has 2, 4, 6, and then 7 electrons. So this is not obeying the octet rule. And that is simply because we don't have enough electrons so that the nitrogen will have an octet, all right? So we call such structures where you have an unpaired electron on an atom, we call it a free radical, all right? So we call these molecules free radicals where one of the atoms have an unpaired electron. And then we have structures such as these where, for example, the boron here has 2, 4, 6 electrons.
I'm not seeing any structures. It's on
okay.
CO2.
All right, let me try this then. Oh shoot. Okay, I know what happened. Let me try. Let me try this. Okay. Okay, can you see now?
Yes.
Okay, good. All right, so I guess I have to go back again. I'm sorry about that. Okay, so this is what I was talking about earlier, right? Nitrogen dioxide. This is the Lewis structure of nitrogen dioxide, all right? You'll notice that there's an unpaired electron here, right? And therefore the nitrogen does not have 8 electrons on its outer shell, 2, 4, 6, and then 1, 7. So we call structures like these free radicals. Free radicals are basically structures where you have at least one unpaired electron, which is, in this case, on the nitrogen atom, all right? So that's one example of a molecule that don't follow the octet rule, all right? Another example is this molecule right here, boron trifluoride. This boron is bonded to 3 fluorine atoms, and therefore this boron has 2, 4, 6 electrons on its outer shell, and therefore, again, the boron does not obey the octet rule. Now, in the case of this molecule, this pair of electrons can be shifted here to form a double bond, and therefore the boron can have 8 electrons. However, if the boron was bonded to 3 hydrogens, for example, then you don't have lone pairs of electrons on the hydrogens, and therefore you don't have the possibility of multiple bonding, which would give boron 8 electrons. And the point I was making by drawing this here is that structures such as this, where you have a deficiency of electrons on the central atom, are very active because they seek out species that it can get pairs of electrons from to satisfy its octet. So for example, if you have a chloride ion here in close proximity, then it will donate a pair of electrons here. You're going to have a double bond here, and now the boron has its octet satisfied, and this would be the resulting structure, all right? So that's another example of a molecule that don't follow the octet rule. A third example, go to the next slide. A third example is this example here, where in the case of phosphorus in this molecule, and in the case of sulfur in this molecule, the atoms have more than 8 electrons, 2, 4, 6, 8, 10 electrons in the case of phosphorus pentachloride, and 2, 4, 6, 8, 10, 12 electrons in the case of sulfur hexafluoride, all right? Now, this can happen in some cases where, as I wrote here, atoms from period, if these are atoms, essential atoms, if they are from periods 3 and higher. So phosphorus and sulfur are both in period 3. So pretty much if you have atoms in period 3, 4, and 5, those are the more common ones, then basically those atoms can actually form structures where they have more than 8 electrons on their outer shell, all right? Okay, so I thought it was important that I show you these. And by the way, the term that is used for such atoms in some chemistry texts, they say that these atoms can expand beyond their octet. And there's a reason for that, which we're going to get into in the next chapter. Okay, here's another example of an atom in a molecule that has more than 8 electrons on its outer shell. In this case, it's boron pentafluoride. And as you can, not boron, bromine pentafluoride. And as you can see in the case of the central bromine atom, it has 2, 4, 6, 8, 10 electrons. And then you have another pair, which is a non-bonding pair. So a total of 12 electrons on its outer shell. Again, in this case, bromine, which if I'm not mistaken, is in period 4, can expand beyond its octet to have more than 8 electrons on its outer shell. All right, so these are all examples of molecules that do not obey the octet rule. Now, let me get out of this here and go to some other, oops, screen sharing has stopped. So I need to do this again. Let me go to here. Okay, so can you see the screen?
Yes.
Okay, good. So I went over this earlier, but since nobody was here, I'm going to repeat this again. So if you recall, before we left last class, I introduced this formula to you, right? This is a formula for calculating the formal charge of an atom in a molecule. And that formula is formal charge is equal to group number minus half the number of bonding electrons minus the number of bonding electrons, all right? I'm sorry, the number of non-bonding electrons. So this is a formula that you would use to calculate the formal charge of any atom in a molecule. So this formula should be used whenever you're doing any Lewis structure determination. So the example I was working with here is the example of carbon dioxide. And if you recall, the first step in this process is that we count up the total number of valence electrons. So if you go to the periodic table, you'll see that carbon will contribute a total of 4 electrons, and each oxygen will contribute 6 electrons, but there are 2 of them. So the total number of valence electrons contributed by both oxygens will be 12. So 12 plus 4 gives you 16 electrons, which is equal to 8 pairs, all right? So let me erase this here so that you can see how we arrive at this structure. I'm just going to erase this right here. And let me erase this down here while I'm at it. Okay, so we start off. Okay, what's going on here? Okay, why is this not? Okay. So we start off by putting the carbon in the middle. We do it here. And the oxygens on either side. Now remember, we have 8 pairs to assign. So the first pair would go here, bonding pair. The next would be another bonding pair here. So we have used up 2 of the 8 pairs, which means that the other 6 pairs will end up on the oxygens like this, 3, 4, 5, 6, 7, 8, all right? Now, the next step is to calculate the formal charge of each atom in this structure. So the calculation I showed you down here is for the carbon, right? Which is in the middle. So this is the formula that we're using. So for carbon, the group number is 4 minus half the number of bonding electrons. So for this carbon, you have 2 plus 2, 4 electrons. So half of 4 minus the number of non-bonding electrons, which for this carbon is 0. So this gives you a charge of plus 2. So the charge on the carbon here will be plus 2. And then in the case of oxygen, it is the group number. And by the way, you'll notice that the electron arrangement for this oxygen here, for this oxygen, is the same as for the other oxygen. So if we do the calculation for one, it's the same as the calculation for the other. So we can just focus on one oxygen. The group number is 6, if you look it up in the periodic table, minus half the number of bonding electrons. So this here represents bonding electrons. So that's half of 2, minus the number of non-bonding electrons, which for each oxygen is 2, 4, 6. So we have 6 here. So when you work this out, this gives you minus 1. So that means that each oxygen has a minus 1 charge, while the carbon in the middle has a plus 2 charge. So when we have a situation like this where we have 2 atoms that are negatively charged bonded to an atom which has a plus 2 charge, what will happen is that this pair of electrons, lone pair, will be attracted towards the carbon and therefore form a bond right here. This negative charge will cancel out one of the 2 plus charges, and the same thing will happen on this side. And this negative charge will cancel out the remaining plus charge. And therefore, when this works out, you're going to end up with this final structure. All right? So therefore, this here would be the final answer if you're asked to draw the Lewis structure of carbon dioxide. All right? Okay, any questions about this example? Any questions? Any questions? Okay, let's do another example. What shall we do? What shall we do? I'm trying to think of another. Okay. Let me clear this here. Okay, suppose you're given, okay, I did CO2 before. Let's try NO2 minus, the nitrite ion. All right, So what would be the first step in this process? Based on what we have done before in the other examples previously. What would be the first step?
Figuring out how many electrons are in nitrogen and oxygen.
Yeah, how many valence electrons? Whoops, what did I do here? Okay, let me go back to 100. Oh, let me go to 100. I just want to make it more larger to occupy. Okay, can't do that. Okay, so yes, so what would be the number of valence electrons that nitrogen would contribute?
2.
Nope, you have to go to the periodic table and look up the group number. So what's the group number for nitrogen?
5.
Correct, 5. Sorry about that. So 5 electrons would be contributed by nitrogen. What about the oxygens?
6.
6, but there are 2 of them, right? So that means you have to multiply by 2. So therefore, the total number of electrons contributed by the oxygens would be 12. Now you'll notice there's a negative charge here, right? We have to take that into account. And the way we do that is that for every negative charge that is present on the structure, you add an electron. For every negative charge that is present in the structure, you add an electron. So for the negative charge that is present, we add 1 electron. So this gives a total of 5 plus 12, 17 plus 1, 18 electrons, which will equal to 9 pairs, all right? So the next step is to put the nitrogen in the middle, surrounded with the oxygens. We have 9 pairs to assign. The first 2 pairs would go here and here, then 3, 4, 5, 6, 7, 8, all right? So we have assigned 8 of the 9 pairs so far, which means that the 9th pair will end up on the nitrogen, all right? But of course, we cannot stop there because we have to calculate the formal charges. So let me remind you of what the formula for formal charge is. It is the group number of the atom minus the number of bonding electrons, minus half the number of bonding electrons, I'm sorry, minus the number of non-bonding electrons, all right? So let's start with the nitrogen. How would we calculate the formal charge for the nitrogen? Anybody? What's the group number of nitrogen?
5.
5, yep. Minus half the number of bonding electrons. So if you look at the structure here, the number of bonding electrons for the nitrogen will be 2 and 4. So we're going to put 4 here. And then for the non-bonding electrons, we have 2 here for the nitrogen, so we're going to minus 2. So 5 minus 2, that's 3 minus 2, that gives you plus 1. So there'll be a plus 1 charge on the nitrogen, all right? And then we do the same thing for the oxygen. The group number is 6 minus half of 2 minus 6, because remember, we're doing the calculation for 1, which is the same as the other. And when you work this out, you're going to get minus 1, all right? So each oxygen in this structure will have a minus 1 charge here and here, all right? So in this case, which is different from the carbon dioxide case that we saw earlier, we have 2 atoms that are negatively charged, but the central atom has only 1 plus charge. So what's going to happen in this case is that only 1 pair of electrons from one of the oxygens, let's say this one, will be attracted to the nitrogen, and a double bond will be formed here. So in this case, the final answer is going to be O, and then you have 2 lone pairs. You have a double bond, you have N, you have a lone pair here, and you have single bond here, and then this oxygen will still have a negative charge. So this would be the final answer for the Lewis structure of the nitrite ion, all right? And one thing I want to point out here, you'll notice, remember you started off with a negative charge here. In the case of the nitrite ion, you're still going to have the negative charge here. It's going to be on one of the oxygen atoms here, all right? So that's basically the how you determine the Lewis structure for the nitrite ion. All right. Any questions about this? Any questions? Okay, so let's do another example. Let's see here. This example is going to be, okay. So let me clear this. And the example we're going to look at here is the carbonate ion. All right. So let's see if you can do this one on your own without any help from me. So what would be the first step? Anybody?
How many valence electrons are in carbon?
Okay, so how many valence electrons would carbon provide?
4.
Good, okay. And then for the oxygens, how many valence electrons would each provide?
6 and then times 3. So that's
Okay, so it's 18, right. And then we have to take into account the -2 charge. So how do we do that?
you do +2 with the 3, so it'll be 5.
I'm sorry, repeat that?
It's +2 with the 3, so it's 6 times 5 now.
I don't understand what you just said, I'm sorry.
Don't you do like 3 plus 2?
No. You just add 2 electrons to the total. Remember I said for each negative charge, you add an electron, right? So basically, in addition to the 4 and the 18 that we talked about before, because you have a -2 charge, you have to just simply add 2 electrons. All right? So this gives a grand total of 24 electrons, which is equal to 12 pairs. All right? So we have 12 pairs to play with. So we put the carbon in the middle and surround it with the oxygens, right? And then we do what? What do we do next?
Start putting your pairs together.
Okay, so remember, we have 12 pairs. So where would we put the first pair?
Between the carbon and oxygens.
Exactly. So first pair goes here, second pair goes there, third pair goes there, and then what?
Then start putting them around the oxygens.
Okay, so 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have used up all 12 pairs, all right? So the next step would be what?
To find the charge?
The formal charges, right? So let's do the formal charge for carbon, firstly. So that would be equal to what?
4.
4, which is a group number, very good, minus half of? Half of the number of bonding electrons, right?
So 3.
So, no, remember, each line represents 2 electrons. So what's an,
6.
exactly, half of 6 minus the number of non-bonding electrons. There are no non-bonding electrons for the carbon, so that's 0, right? So that's, I'm sorry? Oh, you're going to say something, Mr. Turner?
No, sir. I didn't say
Oh, okay.
anything.
Oh, I thought I heard your voice. Okay. So this works out to give you +3, all right, for the carbon. Let's do the same thing for the oxygen. The group number is what?
6.
6 minus half of, now remember, we're doing the calculation for 1 because it's the same as the others, right? So if you focus on 1, let's say you focus on this oxygen right here, is 6 minus half of what?
6.
Nope. Remember, it's half of the number of bonding pairs. Or bonding electrons, I should say. Half the number of bonding electrons.
Then 2.
Exactly. So 2 here, minus the number of non-bonding electrons, which is
6.
6. So that should be equal to -1. So this is -1 -1, -1, and +3, all right? So here we have a situation where we have 3 negatively charged oxygen bonded to, oh, by the way, hold on, I think I made a mistake here. This is not +3, this is +1. How did I make that mistake? Did I got it? 4 - 3 gives you +1. I don't know what I was thinking. So this should be +1. All right, so let me erase this here as well. So this should be +1 here. Okay, so here we have a situation where we have 3 negatively charged oxygen, each carrying a -1 charge, and we have a carbon here which has a +1 charge. So what do you think is going to happen next?
You have to move one of the minus charges over, so it's like a double pair.
Exactly. So you're going to move a pair of electrons to here. This negative charge will cancel out this plus charge. So therefore, your final answer is going to be, let me see if I can scroll down here. Oh, no, there's no more space. Okay, so the final answer is going to be O with 2 lone pairs, double bonded to carbon, single bond to O, minus, and this will be bonded to O, minus, and that will be the final answer. All right? Okay, any questions about this one? Any questions? Any questions? Okay, let me try another one. Let's see, what shall we do? What shall we use? Okay, let me clear this. And let me write here. Okay. All right, SO3, sulfur trioxide. All right. Okay, so what would be the first step in this case?
Finding the valence electrons of sulfur.
Okay, so sulfur would contribute how many electrons?
Six.
Okay, and oxygen will contribute how many each?
6 times 3.
Times 3 gives you 18. So this gives you a grand total of 24 electrons, which is equal to 12 pairs. So we put the sulfur in the middle, surrounded with the oxygens. All right, and then we put the bonding pairs, 1, 2, 3, and then the non-bonding pairs, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then we calculate the formal charges. For sulfur, that would be, how do we calculate the formal charge for the sulfur atom here?
6.
6 minus
Half.
half of
6.
6 minus
Minus 0.
0, exactly. So this gives you +3, all right? And then for each oxygen, again, it's the same calculation for each of them. It would be what? How would you calculate the formal charge?
6.
6 minus
Half
half
of
of
2.
2 minus,
6.
and that gives you -1. So the sulfur has a +3 charge, and each oxygen has a -1 charge. So what do you think is going to happen next?
Each electron gets moved to
You mean
form
like
a
this?
Yes.
Okay, like this, and like this. So the final Lewis structure is S double bond O, double bond O, double bond O. All right? And we know that because sulfur can have more than 8 electrons on its outer shell, because sulfur is in period 3, all right? So therefore, as you can see here, it's 2, 4, 6, 8, 10, 12. So therefore, that can happen in the case of sulfur, all right? So this would be the final answer. Sulfur trioxide's Lewis structure would be this. All right. Okay. Any questions about this one? Any questions? Okay. So I'm going to put a formula on the screen. And I'm willing to bet that you guys are going to screw up on this one. The nitrate ion. Okay, so what's the first step?
The valence electrons for nitrogen,
And that's how many?
5.
5.
Okay, so nitrogen will contribute 5. And what about each oxygen?
6 times 3.
6 times 3 equals 18. And what about the negative charge?
Plus 1.
Plus 1, exactly. So this gives a grand total of 18 plus 5, 23 plus 1, 24 electrons, which is equal to 12 pairs. All right. So nitrogen in the middle, surrounded by the oxygens. Okay, so what next?
You pair the oxygens to the nitrogen.
So 1, 2, 3. Oops, 3. Okay, and then what?
And then put them around the oxygens.
4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So the next step, of course, is to calculate the formal charges. So let's do that for nitrogen. So the formal charge of nitrogen will be equal to what?
5.
5 minus
Half of 6.
6 minus
0.
0. Okay, very good. So that's 5 minus 3, that's plus 2. And then we do the same thing for the oxygen, which would be what?
6.
6 minus
Half of 2.
half of 2 minus,
6.
nope. Oh yeah, 6, I'm sorry. What am I thinking? You're right. So this gives you minus 1, right? So the nitrogen has a plus 2 charge, and each oxygen has a minus 1 charge, all right? Okay, so what's the next step?
You move 2 of the oxygen charges, only 2 of them, to form a double pair.
I knew you were going to say that. No, you can't move 2. You can only move 1. 1 pair would go here, right? Can anybody tell me why it's not possible to move another pair, you know, like this one here, to form another bond? Can anybody tell me why? Why it's impossible for you to move the other pair after moving the first pair?
Would it unbalance it between the third oxygen?
I'm sorry?
Would it unbalance it between the third oxygen?
Nope, that's not the reason.
Is it because it's NO3 minus? And
Nope, that's not the reason. Nobody knows? You remember what I said about elements in period 3 and beyond? That they can have more than 8 electrons on their outer shell? Well, nitrogen is in period 2, right? And if you were to put this pair of electrons here and this pair of electrons here, the nitrogen atom will end up with 2, 4, 6, 8, 10 electrons on its outer shell, which is not possible because nitrogen is in period 2, right? So basically, there's only 1 pair of electrons that can be shifted. Let me erase this here, right? There's only 1 pair of electrons that can be shifted, so I'm shifting this one here. So therefore, the final answer is going to be this. Double bond N plus charge, because when this negative charge cancels out one of these 2 plus charges, you're going to be left with a plus 1 charge, and then you're going to have O minus, and then O minus. So this here, folks, will be the final answer. All right? That will be the final answer for the Lewis structure of the nitrate ion. All right? And I want you to notice that the total net charge for this would be -1, right? You have a plus charge and you have two negative charges. So the net charge is -1, which corresponds to the -1 that you have here in the original formula. All right? Any questions about this one? Any questions? Okay, so let me do a couple more examples. Suppose you're given, okay, this one should be relatively easy. NH4 plus, all right? So the first step would be what?
Valence electrons for nitrogen,
Which is what?
5.
5.
5, okay. And then for hydrogen, what's the group number for hydrogen?
1.
Right? And there are 4 of them, so times 4. Now we have a positive charge. Now, if you remember, we said every time there's a negative charge, we add an electron, right? So what do you think we do each time we have a positive charge?
Take away an electron.
Exactly. So we minus an electron here. So this gives you a total of 9 minus 1, 8 electrons, which is equal to 4 pairs. We put the nitrogen in the middle, surrounded with the hydrogens. Right? We have 4 pairs to play with. 1, 2, 3, 4. And then we calculate the formal charges. For the hydrogen, that would be group 1 minus half the number of bonding pairs, which is 2 for each hydrogen, minus 0 equals to 0. And the formal charge on the nitrogen would be equal to the group number, which is 5, minus half of 8, minus 0 equals to plus 1. So therefore, there'll be a plus charge on the nitrogen and no charges on the hydrogen. All right? Any questions about this one?
Mm.
Okay, give you a minute, well, maybe 2 minutes. I'll be right back. Okay. Okay, I'm back. All right, so if there are no questions about this one, let me clean this up. And let me put another one. Now, this one is a bit different because in this case, we have 3 different atoms present. All right? Okay, so what would be the first step in this process?
Find the valence electrons.
Okay, so for sulfur, that would be what?
6.
6. And for oxygen, that would be?
6.
And for chlorine, that would be?
Mm.
What's the group number for chlorine?
7.
7. but because there are 2 of them, you have to
Times
multiply this
2.
by 2, so that's 14. Okay, so that's a total of 6 and 6, 12 plus 14, so that's 26 electrons, which is equal to 13 pairs. So we put the sulfur in the middle, surround it with the other atoms, because sulfur is the least electronegative element. So we start assigning our bonding pairs. Now remember, we have 13 pairs to play with. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which means that the 13th pair will go on the sulfur atom. Excuse me. So the next step would be the formal charges calculation. So let's do the calculation for sulfur. So how do we calculate the formal charge of sulfur?
6.
Okay, 6 minus half of
6.
6 minus,
2.
exactly. So that's 6 minus 3, which is 3 minus 2. So that gives you +1. So there will be a plus charge on the sulfur. And let's do the calculation for oxygen. So the group number is what?
6.
6 minus half of
2.
2 minus,
6.
okay, so this gives you -1. So the sulfur, I'm sorry, the oxygen has a -1 charge. And then we do the same calculation for the 2 chlorine atoms. So it's the same calculation for each of them. So the group number for chlorine is
7.
7 minus half the number of bonding electrons, which is
2.
2 minus the number of non-bonding electrons, which is
6.
6. So that's 7 minus 1. Hold on, 7 minus 1, that's 6 minus 6. So therefore, there are no charges on the chlorines, all right? So what do you think, excuse me, what do you think the next step is?
To move the oxygen.
Move the pair of electrons from the oxygen down here. This negative charge will cancel out this plus charge. So the final answer is going to be Cl bonded to S, double bond O, bonded to Cl. So this here will be the final answer. All right. Okay. So I think I've done enough examples of different molecules and ions that you can follow. And based on these examples that we did, you should be able to pretty much draw the Lewis structure of anything that is thrown at you. All right. But of course, this takes practice. So I would strongly recommend that you, go to your textbook and look up some Lewis structure problems and practice those so that you get a good feel for this particular area. Okay, any questions about this or any other example or anything in general with respect to Lewis structures? Any questions? Okay, so let's go back to PowerPoint. Okay, so the next thing we're going to talk about here, bring this down here. And we're going to talk about the concept of electronegativity. So the definition of electronegativity is given right here. It is a measure of the ability of an atom to attract.
PowerPoint.
Oh, shoot. I keep messing up on this. Sorry about that, folks. Okay, can you see my PowerPoint now?
Yes.
Okay, thank you. So as I was saying, the definition of electronegativity is the ability of an atom to attract bonding electrons to itself, all right? So the greater the attraction of an atom for bonding electrons, the greater would be its electronegativity, all right? So what you'll find is that if you look at different atoms in the periodic table, you'll see that the trend in terms of electronegativity is that it increases as you go from left to right of any period and from bottom to top of any group, all right? So that's basically the how the trends appear. Now, a scientist by the name of Linus Pauling, many decades ago, came up with a scale for measuring the electronegativities of different atoms. And I think, if I remember correctly, his scale was based on thermodynamic data. So what you're seeing here on the screen is basically Linus Pauling scale. You may see some other different scales in different textbooks, but this is the one that we'll be using for our purposes in this course. And as I said before, as you go from left to right of any period, right, the electronegativity increases. So metals typically have relatively low electronegativity values. Typically the values would be less than 2, and then 2 and above would be either metalloids or non-metals, all right? And you'll notice that of all the elements, fluorine has the highest electronegativity value, which is 4.0, while boron has the lowest, I'm sorry, not boron, lithium. No, actually francium has the lowest electronegativity value, all right? Okay, so that's basically a summary of the electronegativity values of different elements. Now this concept will become important when we look at certain properties exhibited by molecules. But before we get to that, let's look at some definitions here. Now, if you have two identical atoms that have the same electronegativity, what that means is that they will both attract the shared electrons equally, right? So if you have two atoms, like for example, 2 chlorine atoms or 2 hydrogen atoms, then basically when they form a molecule, they will have the same level of attraction for the shared electrons, right? So the bond that is formed will be considered to be nonpolar, right? So we call that a nonpolar covalent bond, all right? So here's one example, chlorine, 2 identical atoms, a pair of electrons is shared between them. Because these atoms are identical, they will have equal attraction for the shared electrons, all right? In fact, all homonuclear diatomic molecules have nonpolar covalent bonds. So all these molecules here, which you should know about, which are bimolecular, are all nonpolar because they all are identical, sharing the same electrons, and therefore they will have equal attraction for the shared electrons. So therefore, they all have nonpolar covalent bonds, all right? Now, if you have a situation where you have 2 different atoms and there is a great attraction of one atom over the other for the shared electrons, then basically what that means, obviously, is that the electrons will be shared unequally, and that bond will be called a polar covalent bond, all right? A good example of this is the hydrogen chloride molecule, because chlorine is more electronegative than hydrogen, so therefore chlorine will have a greater attraction for the shared electrons, right? Now, one way of representing that shift in electrons is using this symbolism here, an arrow with a cross at the tail of it. It shows you the direction in which the electrons shifts in a bond from the less electronegative element to the more electronegative element, all right? Another representation that is used is this one right here, right? This is indicating that because the electrons are shifted towards the chlorine, there will be an accumulation of negative charge on the chlorine atom. So this chlorine atom will have a partial negative charge, not a full negative charge, because you don't have the full transfer of electrons over to the chlorine. You have a shifting of the electrons over to the chlorine, and therefore there'll be a partial negative charge for the chlorine atom and a partial positive charge for the hydrogen atom, all right? So these are 2 different representations of a polar covalent bond, all right? So that's polar covalent. Okay, so if the electronegativity values are so different between the 2 atoms that are bonded to each other, then we call, and if the difference is so vast that electrons are transferred from one to the other to form ions, then we call this an ionic bond, all right? So this typically happens, of course, between a metal and non-metallic atoms. So for example, if you have sodium bonded to chlorine, then basically that would be an ionic bond, right? That is formed between the sodium ions and the chloride ions. And we talked about that in an earlier chapter. Okay, so how do we, well, before we get to that. So this model here is showing you basically the difference between a nonpolar covalent bond and a polar covalent bond. In the case of a nonpolar covalent bond, the shared electrons are evenly distributed between the two atoms. In the case of a polar covalent bond, you have basically a shift of the electron pair towards the more electronegative element. In this case, the chlorine will have a partial negative charge and the hydrogen will have a partial positive charge, all right? So that's what happens in the case of a polar covalent bond. And what you see here down here is called an electrostatic map of the hydrogen chloride molecule. It's basically a model that is used to show the separation of charge within the bond where the electrons are shifted towards the more electronegative atom. So the red region here represents the negative charge accumulating around the chlorine, while the blue region here represents the fact that the hydrogen is electron deficient and therefore has a partial positive charge. Okay, so how do we tell whether or not a bond is polar or, well, polar covalent, non-polar covalent, or ionic? Well, if you look in different textbooks, they have different criteria, all right, for establishing the different types of bonds. The criteria that we're going to use is what I'm going to write down. Where am I going to squeeze it? Let me write it down here. In fact, let me get out of this here and let me go to my writing pad here. And I guess I have to go to new share. And okay, can you see my screen now?
Yes.
Okay, so I'm going to create a little table here. Okay, how should I do this? I'm going to say bond type for one column. And in the other column, I'm going to have the difference in electronegativity values, all right? Now, if, oh, you know what? Let me do this the other way. I'm sorry. I think it's more sensible to do it the other way. Okay, so difference in electronegativity values and bond type on the right, all right? So if the difference in electronegativity values between the two atoms range from 0.0 to 0.4, then the bond type is essentially non-polar covalent, all right, for most intents and purposes, all right? So if you have two atoms, a good example is carbon to hydrogen. So let me create another table here with example, all right? So for example, a carbon to hydrogen bond is essentially nonpolar because if I remember correctly, and let me go back to the PowerPoint here. I'm trying to find the table. Carbon is 2.5, hydrogen is 2.1. So carbon is 2.5, hydrogen is 2.1. So the difference is 0.4, right? So therefore the carbon to hydrogen bond is basically nonpolar covalent. Now, if the difference goes from 0.5 to 1.7, then this bond is essentially polar covalent. Now, an example of that would be, let me see if I can find it here. If you have, let's say, a bond between let's say, sulfur and chlorine. So sulfur bonded to chlorine, all right? Now, according to this, sulfur has a value of 2.5 and chlorine is 3.0. So the difference in electronegativity values would be 0.5, right? So 0.5 would fall within the range here. So therefore that bond is said to be polar covalent. And then finally, if the difference in electronegativity values goes from 1.7 to higher, then the bond is essentially ionic. So for example, in the case of sodium chloride, sodium has a value of 0.9, chlorine has a value of 3.0. So the difference in electronegativity values would be 2.1, which is obviously greater than 1.7. So therefore, that bond would be ionic. All right. So this is a criteria that we're going to use in this course to determine whether or not a particular bond between two atoms is either nonpolar covalent, polar covalent, or ionic. All right. Okay. Any questions about this? Any questions about electronegativity and the related bond types? Any questions? Okay. Let me get back to this. In fact, hold on, let me see here. Okay, can you see my screen?
Yes.
Okay. Okay, so the next topic, let's go down here. Okay, what time is it, by the way? I'm losing track of time. Okay, you know what? Let me stop here for today. And then we'll continue from this page here, which talks about resonance. Before you leave, you may have noticed I've posted, what was it? Quiz number 4? So if I'm not mistaken, it is due on Friday. So make sure that you download it and complete it. Again, if you have any questions about, any problems on that particular assignment, feel free to contact me via Skype during my office hours, and I can help you with that. All right. So make sure that you get to that so that you can complete it by the deadline. I think that's all I have by way of announcements. Let me see here. Any questions you guys have? Any other questions? General questions, whatever?
No, sir.
No? All right. Well, that's it for today. So I'll see you guys on Thursday. All right.